Sheshala. Welcome to Easy Vedic. In this class, we are going to learn about another error control mechanism is nothing but error detection. So, let us get into the topic what is meant by error detection. See, error detection is another type of error control mechanism or another possible way to control the errors or to detect the errors caused by noise or other impairments during transmission from transmitter to the receiver or sender to the receiver. Here, we can detect the errors. We can detect the errors. In the previous class, we see that error correction mechanism only single bit error we can eliminate by using that error correction mechanism. In this method we have to detect different type of errors, means multiple errors or burst errors we can detect in this error detection technique. See, the error may comes in any reason, nothing but an noise, or crosstalk or unnecessary data comes into our data or frame crashing. So these are the different type of impairments we have to occur error in our data, See, there are different type of techniques we have in error detection. So parity check, checksum, CRC. Parity check, checksum, CRC. CRC stands for cyclic redundancy check. These three are the main techniques to detecting errors in the frames. These three are the main techniques to detecting errors in the frames. The first one is parity check, checksum, CRC, cyclic redundancy check, and it is the very efficient error detection mechanism to detect the errors in our frames. Let us know about each and everything here. Let us know about each and everything, every error detection mechanism, how it works, how can we detect the errors by using these three mechanisms, right? So the first one, parity check. We also know that even parity, odd parity, we have a parity bits. Even parity means we have a even number of words, we consider we get a parity bit 0, or odd number of ones we'll get a parity number is a 1. So this is a parity check. So here we are adding one parity bit to our data unit, one parity bit to our data unit. So it will indicate that we have a even number of ones in our, means in our data unit we have a even number of ones. It indicates a 0. Okay, we have a odd number of ones, it indicates a 1. So this is an parity bit or parity check. So when we have a even number of ones and the parity bit is also indicate 1, means there is an error occur in our data bits. Okay, there is an error occur in our database. That is the main thing. So the parity check, by using this parity check we identify whether the error is occur in our data or not. Okay, but this is not an efficient thing to detect the errors. We can easily identify that is there any error occur in the data frame or not, we can identify that. But this is not an very error efficient error detection technique to detect the errors, right? The next one is checksum. The checksum is a block of code. The checksum is a block of code. So here we are using some algorithm to the data blocks. Here we are using some algorithm to the data blocks, and we are adding this particular, after done all these calculations we will get one checksum. We will get one checksum that will be appended to the original data bit, that will be appended to the original data frame or data unit, right? See, let us see, this is a block code method. This is a block code method where a checksum is created based on the data values in the data blocks, based on the data values in the data blocks. So this checksum creation will be generated at the place of sender. The sender generated the checksum and the receiver received that checksum and calculate that particular data units what the receiver receives. If the match indicates um, if it will the checksum will get all the zeros, there is no error occur in the data. Otherwise there is an error occur in the data. Okay, so it's a block of code and we are applying some algorithm here, and the generated checksum is appended to our original data frame. See how we can generate a checksum. What are the different type of algorithm you are using our data blocks to detect on one type of error in our data unit, right? So sender side, receiver side. This is on sender side and receiver side. The sender as the segment using one's complement arithmetic means here we are using 1 to the actual data to get the sum. So after that, the finally it will create the checksum, that is the last data frame. The last data frame. Here, remember one thing, if you apply this type of algorithm to the data values, each and every frame contains 8 bits compulsory. Each and every bit contains 8 bits. Each and every frame contains 8 bits, right? So receiver, at the receiver side also same process will be done, but the only the difference is the sender generated the checksum and receiver multiplied that checksum to the original data, and finally it get the checksum value. It will get all the zeros. There is no error in our actual data. Otherwise error will occur in our actual data. See, let us take one example. Suppose that the sender wants to send 4 frames, each of 8 bits, where the frames are. So here I'm taking an 4 frames and each frame contain 8 bits. I already discussed this checksum in a previous OSA reference model, right? Okay, checkpoints. Checkpoint. Each and every packet we have a checkpoint. Like the checksum also, we are is a block of code and one algorithm is applying to our data units to get a checksum to identify this is the reliable data or not, or whether the error will occur. We can detect that, right? See, let us see the problem how the checksum is generated at the sender side. Okay, so how the checksum is calculated in the receiver side, how will it get all the zeros? That data is an reliable data without error is occurred in our data while transmitting from source to destination, right? So let us talk about that. See, this is an problem. So I take the 4 frames. I already wrote frame 1, frame 2, so frame 3, frame 4, and this is an actual process, right? So I'm adding first 2 frames. I am adding first 2 frames. So I'll get one carry. So this is an addition. So here I'm adding 1 to the sum. What I get the sum by adding these 2 frames, I'm adding one extra one's complement arithmetic to the sum. We will call this as an partial sum. The output will call it as partial sum. So I'll get 0 triple 1 0 triple 1. So add frame 3. Add frame 3 to this particular sum. Add frame 3 to this particular sum. So I'll get another sum and I am adding the one's complement arithmetic. So I'll get another thing. I am adding frame 4 here. Okay, like that I am doing this process. Okay, these are the this is the final sum I get for entire 4 frames. This is the final sum. I'll get entire 4 frames. 0 double 1 0 double double 0 1 0 double 1 0. So this is an entire sum. So I'm doing an ones complement here. I'm doing an ones complement 1101 double 0 double 1. 1101 double 0 double one. So this is the value, nothing but we will call it as checksum, is generated by the sender. Is generated by the sender. So for these four frames, I will add checksum. I will append the checksum value to these frames, and it will also called as the frame 5. Frame 5 means the checksum value. The checksum value. So let us see at the receiver side how the particular frames are calculated with the checksum. See the actual data, the frame 1, in the frame 1, see the sender side at the receiver side, observe that clearly. The frame, okay, same thing received. Okay, frame 2, 1010. Okay, so there is no error, there is no bit change in these particular frames. So add that, I'll get one value. So add one's complement arithmetic, get a partial sum. Add frame 3. So the receiver side frame 3, sender side frame 3, observe. So this is the frame 3, this is frame 3, this is frame 3. Okay, 4140, 4140. Okay, there is no error, there is no error. Okay, so I am adding here and get one sum. Okay, add this sum to frame 4. So frame 4, double one, 4 zeros, double one, double one, 4 zeros. Okay, in this frame 4 also we don't there is no error occur here. Okay, I'll get one sum. I'm adding one's complement arithmetic, I'll get the actual sum. Here, after calculating all the frames, finally I will add the what the sender sent the checksum value, that will be added to the original sum, means entire sum. So I am adding checksum. Add checksum here. See, add checksum. I am adding checksum. I'll get this, and I am doing one's complement. I'll get all zeros. I'm doing one's complement to the value what I get when I add a checksum to the original value. So here I get all the zeros. That means there is no error occur in a particular data. The receiver received that data. The receiver received that data. So this is the process how the checksum is generated, how the algorithm is applied to a particular frame. Okay, the in the sender side and the receiver side or the both, but the only difference is at the receiver side we add the checksum value to the what they calculated entire sum, the last sum. So I'm using one's complement here, I'm using a one's complement here also. Okay, this is an problematic. So we can solve different type of examples also. Not only this, we can consider any type of data. I'm taking in 4 frames with 8 bits. You can consider any type of data also. So just to remember the steps, how the sender side will calculate, how the receiver side will calculate. Okay, so just remember the steps. So these are the steps of sender side and the receiver side. Sender sides, n segments, m bits. N segments will have n segments and m bits. So any number of segments we can run. I'm taking in 4 frames just as an example. You'll take in 5 frames, 6 frames or 7 frames. But the last frame we will get an checksum. Okay. Add all the segments. If carry is 1, then add it to the LSB of the sum. Checksum is a complementary sum. Message plus checksum. Here the sender said these are the steps we have to generate a checksum. We have to follow these steps. Receiver side, add all the segments. If carry is 1, then add it to the LSB of the sum. Checksum, a complementary sum. If the result is zeros, then the message will be accepted by. So if the result is 0 means when I add checksum, see here, when I add checksum to the complementary sum, what I get adding all the frames, the last sum, we are adding checksum to the last sum. So we'll get all the zeros, then the message will be accepted by. We'll get all the zeros, then the message will be accepted by, because there is no error occur in a particular data frames. Particular data frames. So this is the second detection technique in error detection. Okay, we can detect the errors by using this process. Okay, next, the third one, the most efficient error detection technique today we are using right now. Okay, we are using So CRC, cyclic redundancy check. So very very efficient algorithm. How we can detect the errors by using a CRC. Okay. Let us see also one of the problem. First of all, before going to the problem, just we have to know what is meant by CRC. What are the type of technique we are using in CRC, right? Okay. So this is a problem. Cyclic redundancy check. The CRC is a different approach to detect if the received frame contains valid data or not. The CRC is a different approach to detect if the received frame contains valid data or not. So this technique involves binary division of the data bits. Binary division of the data bits. Okay. Here, the divisor is generated using polynomials. The sender performs a division operation on the bits being sent and calculates the remainder. Here, we'll get and one we are doing an one type of process, nothing but an division process. So this divisor is to do a division. We are providing one divisor, or we can call it as a CRC generator. CRC generator to calculate the CRC bits. Okay, to calculate the CRC bits, we are using one type of divisor. That means that we can call it as a CRC generator. Okay. So the divisor we called as an CRC generator to calculate a particular CRC bits that will be appended to the original data. So here the code here actual data bits plus the remainder is called code word. The remainder is nothing but an CRC bits. The remainder is nothing but an CRC bits at the sender side. Okay, so let us see the example, get one clarity about an CRC, how the data will be calculated by using a CRC generator, how we'll get an CRC bits, how the division will go. Just see the example, we get a clear clarity about this. Okay. Okay. See, cyclic redundancy check. So what are the main parts we need means to calculate CRC data, the actual data bits, CRC generator with nothing but an divisor, CRC bits. So to generate CRC bits, that will be appended to the original data. CRC generator. CRC generator will contain n bits. Okay, n bits means, for example, I am taking the divisor with 4 bits means the CRC bits, after calculating this divisor to the original data, will generate a CRC bits that will be n minus 1 means 3. Okay, if the divisor has 4, the CRC bits will get an 3. If the divisor has 5 bits, the CRC will get an 4 bits. So here the CRC generate contains n bits means the CRC bits will get an n minus 1. Let us see the formula to generate a CRC bits. Let us see the formula to generate a CRC bits, the actual CRC bits. See, CRC bits is equal to data plus n minus 1 zeros. N minus 1 zeros. N minus 1 means you'll consider the CRC generator as n bits, no? Okay, n minus 1 zeros. Put if you take a 4 bit CRC generator, I'll put an 3 zeros here. Otherwise, I am taking as an 5 bit CRC generator, I'll put 4 zeros. That's why I'm writing here n minus 1 zeros. N minus 1 zeros. Data plus n minus 1 zeros divided by CRC generator. While calculate all these, we'll get data plus CRC. We'll get the output data plus CRC. At the receiver side, what we have done? This is actually sender side. This is sender side. At the receiver, what is the process? So data plus CRC by CRC generator. Data plus CRC means we already generated CRC bits in the sender side. So we will add that CRC bit to the data and that will be divided by a CRC generator or a divisor. We call it as divisor. So we will get an output 0 means Three zeros. Three zeros means here I am taking a CRC generator as 4 bits and I get an CRC bits is 3 bits. That's why I'll get an 3 bits here, 3 zeros. Okay, the remainder will come and 3 zeros. So the data is not corrupted. We'll finalize that the data is not corrupted. There is no error occur in our particular data. Let us take one example here. Uh, okay. So I'm taking one example. I'm taking one data bit that is 101101. 101101. Okay. So here there is no mandatory that each and every data frame contains an 8 bits. We can take an 6 bits or 4 bits or 8 bits or 10 bits or 12 bits, whatever it may be, to generate the data. Okay. I'm taking CRC generator as 4 bits. 4 bits. So already we know that if the CRC generator is n bits, the CRC bits are n minus 1 bits, nothing but n 3 bits we'll get. We'll get 3 bits. We don't know that actual thing. Let us see the process. This is the process. So I substitute in the formula data plus n minus 1 zeros. Previous formula at the sender side. This is an sender side. So this process is an sender side, right? Okay, 3 zeros divided by CRC generator or divisor. So I will append this 101101 by 1101. See how the division will get. We are using an XOR operation. XOR operation. In this we are dividing the each and everything and we are using the operation is an XOR operation. See, XOR operation means if the different bits we have, the final value is 1. If the same bits we have, the we will indicate 0. We will indicate 0. Different bits is 1, same bit is 0. See, I will use an XOR operation. So 1 1. Let us see. I will zoom it. Okay. So this is an first 4 ones. So divisor is 4 ones. That's why I am taking the first 4 bits. Okay. First 4. So I am doing an XOR operation. This first 4 bits. So 1 1. So same bits, right? I'll get 0. 1 0. Different bits 1. Different bits 1. So same bits 0. So here just leave the left side zeros. Just leave the left side zeros. Okay. So I'll get a 1110. So just see here the divisor is 4 bits. You have to substitute 4 bits, 4 bits, 4 bits in every step. Okay. So I'm adding here. I'm borrowing 1 0, right? So I'm adding again. I'm doing XOR operation. I'll get an 3 zeros 1. So I'm ignoring the left side bits here. So I'm borrowing 1 0 another 0. Okay, 4 bits. I'll get in 4 bits. So I am adding with an CRC generator. I'll get total 4. Okay. So I have only one bit, that is 0. Just leave the left side 2 zeros and I know we know that the CRC will be generated 3 bits. Consider these 3 bits 0 1 0 as CRC bits. 0 1 0 as CRC bits. So this will be appended by an actual data. So data plus CRC. So this is an actual data. This is an actual data and this is an CRC, right? Okay. So this operation or this process is in the sender side. So the CRC is generated by a sender. So this data will be given transmitted to the receiver. This data will be transmitted to the receiver. The receiver also do the same XOR operation. If the remainder gets an all zeros, then there is no error occur in the data unit. Otherwise, it will not accepted by the receiver. There will be error occur in the data unit. Let us see that thing also. So this is an receiver side. I'm zooming. So this is an receiver side. Okay. So what the sender transmit the data with the CRC data. This is a data plus CRC. See, the last bits are 010. We'll get an CRC bits is 010. So this is an actual data. So there is no error in this data. So we'll get an 3 zeros, right? So I'm doing a same XOR operation here. So same process at the sender side what I did, the same process I'm doing in the receiver side also. So 3 zeros, 1101, last 1101. So all zeros, ignore the left side bits and we'll get 3 zeros. So that is will consider as an CRC. So in this the actual data, okay, so what the sender generated, that what the sender have the actual data, that will be exactly received by the receiver with no errors, with no errors. That's why CRC will come as an 000. Whenever the error occurs, whenever the error occurs is just occurs, how the CRC will get an some number of ones, will get an ones also here. If we get only zeros, that there is no error occur in the particular data, otherwise errors occur in the particular data. See, this CRC, cyclic redundancy check, is mainly used to detect the multiple errors. So the single bit well error is corrected in the Hamming code. So the CRC is used to detect the multiple bit errors. That's why I'm changing 2 bits here. That's why I'm changing 2 bits here. Let us see. So what are the bits I am changing means? See the original data. So this is an original data. So in this place I put 1. So second position, third position. Second position and third position I am changing the bits here. 01 means 10, I put an 10. So I am doing an XOR operation here. I am doing an XOR operation at the receive side. This is an corrupted data. I already wrote corrupted data. So see this, the final CRC at the receiver end is 111. The final CRC at the receiver side is 111. Thus means we can tell this is an corrupted data. This is an corrupted data. Okay, so I'm changing bits here. I'm doing the same XOR operation 1101. So I'll get 4 zeros. So I'm ignoring that. Again, I'm now loading the actual data. So I'm doing the same XOR operation. I'll get 1000. I'll get same XOR operation. So the same. The final CRC is 111. So actually we have to get and 3 zeros with 3 zeros, that indicates there is no corrupted data while transmitting from sender to the receiver. If we'll get any other, instead of zeros, any other value will get, there is an error occur in our original data. So this is an example problem of CRC. Okay, these are the different type of error techniques we are using in error detection. Mainly we are using an CRC for multiple, to reduce the, to eliminate the multiple bit errors. Okay, for single bit error we are using an Hamming code. For multiple bit errors we are using the efficient algorithm, is nothing but an CRC. Okay, this is the example of an CRC. Okay, right? Okay, so in this video we discussed what is meant by error detection, what are the different type of techniques we are using in error detection. Mainly 3 techniques, very important: parity check, checksum, and cyclic redundancy check. We see the examples of each and every technique. I hope you understand. Just calculate in our side also each, and let us take the some one example and calculate this process. Okay, so that will be very easy. So in this video we discussed what is the CRC, what is the checksum, and we solved the different type of problems. Kindly like, share, subscribe Easy BTech for more videos. We'll saw different type of examples and problems in later videos, right? Thank you.